So if we were to take a vial of blood and centrifuge it, we would be able to separate the different components based on their relative densities. And that's what we have here. And so the most dense component of our blood are the formed elements. And more specifically, it will be that of the erythrocytes. So we can find erythrocytes at the bottom portion. They constitute a relatively significant fraction of the formed elements compared to the others. So here we can see we have 5 to 6 million erythrocytes compared to, a quarter of a million at the least of platelets and 5 to 10,000 of our leukocytes. So erythrocytes, or red blood cells, make up a really significant portion of the formed elements, or the cellular elements. And a term that we can use for the erythrocytes is the hematocrit. So hematocrit is the packed cell volume. It's the percentage of the whole blood volume that is composed of red blood cells, or composed of erythrocytes. And when it comes to this value, it can fall within a particular range. I'm not really going to provide the quantitative value because that's not really relevant to our discussion, but I do want to think about the fact that that hematocrit value has been shown to be higher slightly in men as compared to women. And I really just want to think about the physiological reasons why that might be. One possibility is the role that androgens will play, and we'll discuss androgens a little bit further down the line when we go through the reproductive system. But androgens are higher in men than in women, and androgens stimulate erythrocyte production. Another physiological component can be the reproductive age of a woman. And based on that, there will be periodic blood loss due to menstrual cycles, which we'll discuss in more detail later as well. When it comes to the hematocrit value, it has an inverse relationship to body fat, and the average body fat is higher in women than men. So those are 3 different ways in which we would see a hematocrit value being lower in women as compared to men. So those are our erythrocytes. And when we think about erythrocytes, the goal is to transport gases. Okay, so there's movement of oxygen, there's movement of carbon dioxide. And you also want to think about the amount of erythrocytes that we have as well, because we have a ton of them, because we are prioritizing that movement and diffusion of gases throughout the different regions of our body. Now, if we focus on our vial, what we'll see is that the bottom portion of the tube contains the erythrocytes, which were discussed. But then there is this small layer in white here, and this is sometimes referred to as the buffy coat, and that is where we will locate both leukocytes and platelets, and we'll go over those 2 in separate voice threads. Next, we have leukocytes, or white blood cells, and they have a known role in defense and immunity. And when looking at the number per microliter of blood, we can see that they fall within a particular range of 5 to 10,000, with values increasing depending on the needs of the individual. And so this is a connection back to the idea of clonal selection and amplification during an immune response. Now, when it comes to leukocytes, there are granulocytes, which means that if we were to kind of peek into the cell, we would find kind of granular or little punctate stains within them. And there are agranulocytes, those that are lacking in those granules. So we'll just go through the granulocytes as well as the agranulocytes, and the amount of detail that will be provided will be relatively minimal, just because a lot more detail is provided within the immune system content. So when it comes to neutrophils, these are granulocytes, and they are the most abundant type of leukocyte that we have. And they are really aggressive in their attack of bacteria. And so something that is referred to as neutrophilia is going to occur in response to bacterial infections. So you can assess a response to bacterial infection due to an increase in the concentration of neutrophils within the body. There are eosinophils, and eosinophils can secrete chemicals, and those chemicals can weaken or destroy large pathogens. So that would be things like hookworms or tapeworms, things that are essentially too large to go through the process of phagocytosis effectively. Another example of granulocytes are basophils, and these are the rarest of the formed elements. These can secrete vasodilators, and vasodilators are going to change the diameter of blood vessels. Okay, so they'll increase it through dilation. And then there will also be anticoagulants. And there can be release of other chemicals that can help to attract eosinophils and neutrophils to sites of infection. Now, in thinking about the agranulocytes, there are lymphocytes, and lymphocytes was a really significant kind of discussion that took place in the immune system chapter, because when we talk about lymphocytes, we're really thinking about B cells, T cells, and natural killer cells, and these are second to neutrophils with respect to their abundance. And I won't go through those particular cell types beyond the fact that those are examples of lymphocytes. And then there are monocytes, and monocytes can give rise to macrophages. And macrophages are professional eaters, so they're really focusing on that process of phagocytosis. And they are an example of an antigen-presenting cell. Details of that can be found within your immune system content. So to recap, our granulocytes are neutrophils, eosinophils, and basophils. Our agranulocytes are lymphocytes and monocytes. When it comes to this idea of granules, it may be a little bit confusing when looking at the illustration, since it looks like there's particles that are found within the cytoplasm of the monocytes, but they are indeed agranulocytes. Some illustrations depict them with these little stains within the cytoplasm, and some will not. But in terms of their category, you are going to consider them to be agranulocytes. And when it comes to just the leukocytes in general, we are thinking about their overall role as it relates to defense and immunity. But as you'll notice through the level of detail that I've gone through, I'm kind of I've reserved any excess amount of detail because these things have already been discussed. But it is something that you want to consider or think about when you are going through this content, or when you are thinking about connections that can be made between the immune system and the cardiovascular system. When it comes to platelets, these are not actually cells when compared to erythrocytes and leukocytes. These are fragments that come from cells called megakaryocytes, which are just really big cells. And in the process of platelet formation, those megakaryocytes will essentially stick cytoplasmic extensions out into kind of openings, and those openings will be found within blood vessels, and the force or movement of blood flow will start to shear off those extensions. And so the sheared off extensions constitute platelets. When it comes to platelet counts, these can vary pretty greatly, and that is going to be due to varying physiological conditions, and they play a role within blood clotting, and we'll devote a slide to a discussion of how that process takes place later on. So we've gone through our formed elements or cellular elements, and now we'll shift into our plasma. And blood is a type of connective tissue, and connective tissue requires some means of support, and that support is provided through a matrix. So plasma serves as a liquid matrix that supports the contents of blood, and it makes up the majority of blood volume. Now, when we take a look at the things that we find within plasma, there's water, ions, proteins, and then there are additional nutrients that move throughout the medium. Now, when it comes to plasma, the bulk of it is composed of water, and that is going to serve as the solvent. So that's going to help to dissolve the solutes that are found within the volume of blood. When it comes to ions, we will talk about in more detail the role that they play with respect to osmotic balance, and that's a discussion that we'll reserve for the urinary system. And albumin will be another example of a time where we can think about contents of the plasma and the role that they play with respect to osmotic balance too. We won't really go into immunoglobulins because they have already been discussed during the immune system material. But we know from previous discussion that antibodies can play a role in defense through neutralization and interactions that can increase opsonization and things such as that, right? So we're thinking about them as far as defense and immunity is concerned. There are apolipoid proteins which are responsible for lipid transport, and there is fibrinogen which is associated with clotting. So we'll go through these in a little bit. There are also substances that get transported by the blood, and as we would expect, oxygen and carbon dioxide will move through there because we're trying to bring them to different locations within the body. We would expect waste products in addition to that of carbon dioxide, because carbon dioxide is a byproduct of metabolism, to be moved as well. And there are hormones. So we've discussed the role of the endocrine system with respect to moving hormones long distances, and that gets accomplished within the blood, and it's moving specifically within the plasma. So in looking at this image overall, you should have an idea of what all of these different components do. Some you will have more detail than others just through your earlier knowledge from this semester, and some will fill in the gaps for. Do pay attention to the level of emphasis placed on the different components that are found in the blood as far as thinking about how to prepare for exam-related material. And then something that's always important to do is that when you are looking at something like this and you have an idea of what normal expectations are and the role that they are playing within the body serves, if things deviate from homeostasis, if values go up or if they go down, what could that tell us about what the body is trying to do or what it would be incapable of doing? This slide provides us with an opportunity to think about erythrocytes in a little bit more detail. And we can also consider the relationship of form and function as it applies to erythrocytes. And having that foundation helps us to draw conclusions about expected behavior under certain physiological conditions. So when thinking about form and function, there are a few things to consider. One is that erythrocytes are pretty small in size. And so here we have 7.5 micrometers versus 2.5 micrometers, and a micrometer is 10 to the negative 6. So these are pretty tiny. And the idea of having a small size and shape is thought to help optimize or enhance the surface area to volume ratio. That's a concept that was initially introduced within Bio 100, and thinking about how that ratio is important for efficiency of movement of solutes from one location to the next. And if we start to change volume, what impact would that have on efficacy of moving things? What limitations are there on surface area to volume ratio? All those things are pretty relevant here too. Another thing to consider when it comes to an erythrocyte, and we won't go through the maturation process, but by the time we're thinking about an erythrocyte, this is its mature form. And by the time it's matured, it has essentially ejected all of its content. So when erythrocyte is composed, aside from water, with a ton of hemoglobin molecules. So it's composed of hemoglobin and it's composed of enzymes. And really removing all of the other content and filling this shape with a ton of hemoglobin and enzymes helps to optimize the role that erythrocytes play in the transport of respiratory gases. And so with our hemoglobin molecules, we can have oxygen bound. There is also the process of carbon dioxide transport, which can be accomplished through erythrocytes too. So if we eject everything else, then we can prioritize the space that we need for the things that are serving that primary role. When it comes to the fact that these mature erythrocytes are void of organelles, they are anucleate, which means they are lacking a nucleus. They have pretty much no organelles. They lack mitochondria. And if we think back to the role that mitochondria serves within the cells, we know that these are considered powerhouses and they are really integral to ATP production. And that can be accomplished through oxidative phosphorylation if we're thinking about where the majority of that ATP is coming from. Now, in this scenario, we have an erythrocyte that lacks that mitochondria, which means that ATP production can occur, but the mechanism by which it occurs is different. So I will give you a moment to think about what that mechanism would be based on the fact that the cell is lacking mitochondria. And then I'll start a different voice thread with the answer to that. So if you said through an anaerobic means, then that would be correct. And if we're thinking about an anaerobic mechanism, then you would be considering the process of fermentation. And that process allows for production of ATP, albeit it is not as significant an amount as what can be accomplished under aerobic conditions. And that oxygen serves an important role as the final electron acceptor during oxidative phosphorylation. Now, when we consider the fact that the mature red blood cell or mature erythrocyte, whichever term you would like to use, they can be used interchangeably. The fact that it utilizes anaerobic fermentation is a good thing. So we've often thought about anaerobic fermentation, at least in earlier discussions, as something that helps to create ATP, but it's not great because you don't make a lot. You're creating lactic acid and building that up too. But in this scenario, it's highly beneficial to utilize anaerobic fermentation. And the reason behind that is we do not want the erythrocytes to utilize the oxygen that it should be transporting because it's meant to bring it to somewhere else. So in harnessing anaerobic fermentation, we ensure that we're not using the oxygen that the erythrocytes are carrying. So their job is to transport, not to transport and use a little bit of that oxygen along the way. And when it comes to human cells, these are the only ones that are going to carry on anaerobic fermentation indefinitely. When it comes to erythrocytes, they also have structural proteins, and they are cytoskeletal. So there is spectrin and there is actin that's found within the erythrocytes. And these are found on the cytoplasmic face of the plasma membrane. And these cytoskeletal proteins help to maintain the biconcave shape. So kind of how it dips in here in the three-dimensional drawing. And having that biconcave shape and having these cytoskeletal proteins is beneficial because red blood cells are deformable, meaning they're going to twist and turn. They're not going to maintain this biconcave shape as they migrate through the circulatory system. And based on their size relative to that of a capillary, it can only go through single file. And so having this nature of being able to twist and turn allows it to move through the capillary, which has a diameter smaller than the red blood cell itself. It's also thought to help a little bit with durability because, as you can imagine, constantly twisting and turning to make its way through the capillaries can cause some wear and tear on erythrocytes. And erythrocytes do not live forever. They have finite lifespans and they do get replenished. Now, when it comes to the biconcave shape in general, there are a lot of schools of thought regarding the possible functional advantage that this morphology could serve. But overall, it's not resolved yet. So there will be some books that may say that it provides a physiological function. There may be others that say it doesn't serve one. There may be others that say we don't really know. We're simply hypothesizing at this point. So it's thought that the biconcave shape might contribute to surface area to volume ratio. It's also thought that the biconcave shape can help to reduce spinning of the erythrocyte and turbulence. And having those events take place can have a negative impact on blood flow.